My name is Kedareswara Rao. I work at AMD. So these are the few open source contributions I have made. So coming to the Linux kernel contributions, I developed and upstreamed a bunch of DMA and networking drivers. And coming to the Zephyr contributions, I have added support for a custom runner and added port, RPU and APU support for VersalNet and Versal Gen 2 platforms. So the agenda today is, so we'll talk about what is Zephyr and how exactly the twister framework works, and we'll talk about the twister architecture and how to test the twister, and followed by how to add support for a custom runners, followed by Q&A. So before we start the session, so what is the motivation behind this session? So while I implementing the R52 support for VersalNet platform, so we figured out that Zephyr has a lot of test infra, but when we build those tests and dump it one by one on the board, it's like a time-consuming process. Then we try to figure it out to automate that process. Then we figured out that Zephyr has a framework called Twister, using which the Twister can build, run, and collect the logs in a meaningful way, which will reduce the turnaround time a lot. So that's how we integrated the Twister XSDB runner into a Twister. So in this session, we will talk about the Twister internals and then how to add support for an hardware runners. So at the top level, what is Twister? So Twister is an Zephyr RTOS testing framework, especially can run at multiple boards and multiple configurations and multiple socks. Initially, it was developed to address the unique challenges in resource-constrained devices, but later it was evaluated into a robust embedded system, robot solution because of the contributions from the lot of developers. So at the top level, Twister framework can be categorized into 3 stages, like the test suite architect stage and execution pipeline stage and result processing stage. So during the test suite architecture stage, so it's a framework that is built on Python, which executes the tests across multiple boards and platforms. During the execution stage, what it does is it collects all the tests and it executes again at either a real hardware or on the simulator, and results will be aggregated into reports. So during the result processing phase, what it does is the outcomes will be formatted into different file formats like XML, JSON, and HTML, which can be used by the CI/CD pipelines. So at the top level, these are the Twister architecture. So the test discovery happens via YAML configuration, and filtering happens based on the platform and resource and feature tags. And the build happens using the CMake infra and using a Ninja generator. And execution can happen either on the simulator or on the real hardware. And the final step, it collects the results and reports in a meaningful format. So if we categorize the Zephyr in detail, it's like a 6-stage pipeline where discovery, filtering, and build, execute, aggregate, and report. So this is the end-to-end flow diagram at the top level. So basically, it scans the repository, and which is like a discovery phase, and it parses the metadata, which is like a filtering phase, and then it checks for the test case type. If it is build only, it just builds it. And if it is like execute test, then it executes on the board as well. And then once it executes, all the reports will be collected and aggregated, and it generates the reports like I discussed earlier. So what happens at each phase? So during the discovery phase, basically Twister scans the entire Zephyr code base, and it identifies the YAML configuration and parses the test parameters. For example, here if you see, it's like a typical EPROM driver example where it is saying, okay, these are the platforms I am supporting by default, and this regex. So when we run on the board, this is the console output I am expecting. So when the Twister executes this test, it expects this particular print to be available in the log. If this particular print is not available, it by default marks the test as a failure. So each test case can be tagged with a different metadata like hardware, required features, and expected behavior. Coming to the filtering, so there are 4 types of filtering possible. So like platform-specific filtering. So like I would like to, so this particular test case supports only STM32 or Versal, something like that. Then we can mention that platform-specific checks. Similar way, there are features like tag-based filtering. Like, for example, my particular board won't support FPU. Then I can mention that as in the ignore tags, so that when we run twister tests, it ignores all the FPU tests for that particular board. And similar way, if that particular feature is supported, then we can say that in the supported list, we can mention that particular feature, so that when you run the full suite, the relevant test cases will be automatically pulled by the Zephyr twister framework. And similar way, regex pattern is like, if you have some expression like this string, like we discussed in the previous slides, if this particular print needs to be there, then only this test should be marked as pass. So that kind of regex pattern matching also possible. And then there are test type selections like Zephyr supports different types of tests like unit test, integration test, and robot test. So we can select all the types of test. So we can mention that in the test type selection. And coming to the build, so during build, so it generates the test configuration for each test case and then prepares the CMake build environment, and it compiles against the target. So basically, when we see the final executable, it basically linked against the Zephyr RTOS kernel. So first, the Zephyr kernel will be compiled as a .a, and our test case will be linked against that .a. And during the execution phase, the hardware detection happens, like whether it has a serial ports and all those things, and then it deploys the image on the target, and then it monitors the console logs. And resource management is nothing like whether any hardware resets required and all those stuff will be taken care during the resource management phase. And during the aggregate and report, so it collects all the raw test results and it categorizes them as a pass, fail, based on the test case AML configuration. And then it also records the performance metrics like execution, how much time it executed, and how much memory it took to, how much memory the executable took. And also it correlates the test results with the test configurations and platforms. Like in the test case AML configurations, the developer who implemented the test case will say, okay, this is the expected outcome. So then it checks for that expected outcome and mark the test results accordingly. So now we talked about the twister internal. Then the next thing is how to integrate the runners. So there are two different types of runner available, like emulator runner and hardware runner. So the names suggest emulator runner, so which doesn't require any real hardware. So like QEMU or any other emulators where we can dump the ELFs. Similar way, we have a hardware runner, so which executes the tests on the real hardware. So since this session is all about hardware runners, I will talk about the hardware runner. So what does the hardware runner do? So basically, the hardware runner is the component that is responsible for dumping the ELF on the board, and also it optionally can be usable for debugging purpose. So this particular runner can be used by both westflash command and the twister script. So each runner corresponds to a specific hardware like OpenCD and XSDB, etc. So where is this runner implemented? So these runners are implemented in the scripts west commands runner folder. And each runner is a Python module implementing a subclass of Zephyr binary runner. So how to run the test? So this is the sample hello world example. So for example, this particular command, what it does is, it builds the sample hello world application for this Versal 2 RPU platform and dumps it on the board. So it's basically using the XSDB runner. So this is the output, expected output. So there are advanced options also, like for example, if you want to run all the kernel common tests, then we can give the test filter so that it will run all the kernel common tests. Similar way, we can run the tests in parallel, and we can dump the reports onto a particular folder also. So there are a lot of other options also. I didn't cover this in these slides. So how to implement this hardware runner? So hardware runner implementation involves in 3 steps, like Python class creation, registering, and CMake metadata integration. So first step is Python class integration. So we need to implement a custom. So let's talk about a custom class runner. So if we want to implement a custom class, then we need to write that custom class, custom runner class, and in that we need to mention the number of parser arguments. Like each vendor has different ways of loading the ELFs. For example, I need some flash address to load, or I need some reset, or so those are all options can be mentioned in the parser arguments. And then each vendor has their own run implementation. So there we can mention their run implementation logic. And each runner needs to be mentioned in the init file, so that this is like registering of the runner. And then we need to integrate it into a CMake so that boards can use this particular runner. So CMake integration is nothing but, so we need to create some common meta CMake file, and we need to mention the runner name there, so that any boards that are intended to integrate this runner, they can use this particular custom common.cmake file. So after that, so whoever want to use this particular runner, they need to write a config file in their boards where they should list down all the requirements. For example, so the way of loading ELF varies from platform to platform and board to board. So in their particular board configuration file, they need to mention that, okay, how to load this particular dump. So here I provided some example for the XSDB configurations. So the key TKWs is like hardware runners bridges the gap between Zephyr build system and it automates the entire process. So this, like I discussed previously, so the implementation involves, we need to create a board.cmake and a Python runner class. And there is a lot of documentation available in the Zephyr community, leverage them as much as possible. So this is the reference of the XSDB runner. Yeah, that's it.
Yeah, thanks. Nice talk. One question on the configurations, what you mentioned for Twister, right? Mm. Does it have intelligence with, like, say, if it is integrated into Git, based on the files which have changed, can it select only those tests and then run, or it is all fixed in the like runtime? Say, driver A means it will always run.
So it basically fetches from the workspace. So when you execute that /scripts twister command, so based on the commands you pass, it parses that workspace and gets the data from there.
Okay, so it's like a predefined
test?
That's
yes,
what it will
Yes, yes.
Thank you.
Yeah, hi, this is Govind. I'm from Nutanix and I work with CPU enablement. So I do something similar for x86 where we have our internal test framework for hardware validation called Raptor. It's very similar to this, it's also Python based. I just want to know, so how Raptor works is we run Raptor, we generate a build file and image and we flash that onto a virtual machine that then connects to our target hardware, which is, let's say for example, if I'm testing Intel Granite Rapids or AMD Turin or something like that, I will connect it to that machine and then the test will run on my target hardware platform. Now this is running on the VM. So I just wanted to know how is it different on ARM? Like where does the test run? Does it run on the hardware itself or does it run from a virtual machine that connects to the target?
No, the ELF runs on the hardware only. Direct. So there are two types, right? Like I said, there is emulator thing and the real hardware. So based on the use case, either you can run it on the emulator, like if QEMU supports your particular hardware, then we can use emulator. Otherwise, we can run it on the real hardware.
But is there no, for example, if you are testing a hardware configuration that's related to performance, if the test is running on the hardware itself, is there no performance implication? Because, for example, if you're testing RAM utilization, I'm just giving you an example. So won't the test running on the hardware utilize more RAM? Are you accounting for that? If the runner is running on the hardware itself, more RAM would be so. So what about that delta?
I didn't get your
so if you, like I said, in our case, we run the test framework on a VM, right?
No, here basically, so we will build all the executables on the workspace, like basically your host machine. Right. And then you dump the executables onto the target hardware. So basically, so the RAM utilization will be based on your application, right? So I didn't get your question. So.
No, I'm saying when the test is running on the hardware, wouldn't there be a delta because of the test running also? So you are testing a particular component, but what about the Python script that is, or the Python
that
executable that is running?
that shouldn't add any delta, right? So
Okay, I mean, I'm asking you because I don't know.
no, ideally that shouldn't add any delta.
Okay, thank you.
Yeah, hi.
Hi.
So this hardware runner you mentioned is like,
Yeah.
it's like an open OCD
Yeah.
thing. So similar to that, if you need a custom debugger
Yes,
interface,
yes.
so you can do the stepwise debugging everything
Yes.
using your script, right?
Yes.
Okay. Yeah, that was one point. And you had a results page, right, where you were showing. So is that your in-house or something? So
This one?
yeah.
No.
Or this just
No,
displays.
this. No.
Because, yeah, we have the XML and JSON files as
Yes.
report.
Yeah, that report, so Zephyr generated report won't be like this,
Yeah.
but it is like meaningful thing which can be easily decodable.
Yeah, and one more thing is like we have the test case YAML file where you mentioned about that. We also have the sample YAML in the sample section. So both are similar, right? But,
Yes.
But the test case one has all the Z-test related macros, all those things. So the reporting, how it will be different or?
So basically Zephyr has a different metadatas, like, so there is a hardware map metadata, test configuration metadata, and test suite metadata. So there are 3 to 4 different metadatas. So when we are passing those options, so Twister will automatically parses that metadata. So each metadata has their own keys. So based on that, it will match and checks for the corresponding outcome is there or not.
Okay. And one last question is like, since you have already worked on Twister, so did you ever come up with a scenario, let's say we test SPI, let's assume. You have a master, you have a slave. Is there any mechanism where we can do flashing of both the boards and test it?
We can run parallelly, so it shouldn't be an issue.
The thing is like, I want to test the slave mode for now. So maybe my Twister related code will run on the slave. And maybe the master, I'll just do a best flash. Manually I can do that, but will Twister take care of both?
Yeah, so basically each Twister instance, so you can pass any number of tests. So if you want to dump it on both boards, you need to launch the 2 Twister instances.
Yeah, okay, 2 Twister
instances you need to launch.
It's not one Twister that...
No.
That
because each Twister can pass only one runner argument, right? So we can dump on that particular board only. So you have to launch 2 instances.
Okay, so there's no other...
Yeah, it's tightly coupled with the hardware.
Yeah, and the last one more thing is like you mentioned about the emulated simulation or the hardware, right? So I think when we create a pull request, so Zephyr mainline, they run a lot of tests, and that mainly runs on the emulated platform.
Yes.
Such, right? So let's say Quemu, if it supports our hardware, then well and good. But if we need our own simulator to be there, then we can have that provision to install that or something, to add it to Zephyr.
That I'm not sure.
Okay. Yeah. Okay. And that's all. Thank you. It was good talk.
Yeah, thanks.
Hey, hi. Ramna here.
Yeah.
So especially assuming your system, there are several test cases.
Yeah.
So if it has to run on the hardware, it has to flash every time, invoke the test. So it takes a lot of time.
Yes.
So is there any way where we can reduce the number of times it flashes so that multiple tests can be run in one go? Just to reduce the overall...
I couldn't find that option in the Twister, so
Okay.
in my experience, that is not there.
So for every test,
Yeah.
of course, it has to build independently and
Yeah.
download it
Yeah.
and execute.
Yeah.
Okay. Thank you.
One more.
Yeah.
So these runners that you specified, these are the same as the runners defined in the board definition files?
Yes.
Can the same runners be used?
Yes.
All of the runners will...
Yeah, each runner corresponds to a hardware basically. So basically one SOC platform. So for example, XSDB is like Xilinx or AMD proprietary debugger tool. So where we download the helps. So similar way, OpenCD is like STM32 and some other platforms they
so
use.
Like Xilinx is also a runner.
Yes.
So it will take the Twister takes the same set of runners from the board definition.
So like we showed here right in the example, so we need to just pass that -runner and that runner name.
Yeah, so the argument hyphen runner, that
Yeah.
is the same
Yes.
name as in the board
Yes,
support.
yes, exactly.
Okay. Yeah, I mean, there is a default runner. Yeah. Yeah.
So all this data can be mentioned in the YAML file also, and we can pass that using hyphen map option. So there are other options as well.
Okay. Thank you.
Yeah. Thanks everyone.